So now that we know about mean structures and multi-group models, we can look at measurement invariance testing. And then in the next video, I'll conclude with homogeneity testing. So we have our multi-group model. And in this case, we have 3 indicators. We had to scale the latent variable in both groups. We had to scale the factor variance in both groups. Here I did the factor variance now. And we can compute our degrees of freedom. In this case, the degrees of freedom is 0. That means we're going to get a perfect fit. We're going to reproduce both covariance matrices perfectly. Right? So F will also be 0 in that case. But we'll see that we're going to have less or more degrees of freedom as we go on. So what's the goal of multi-group CFA modeling? And I think that's an important question to ask. I think for many people the goal is just measurement variance. I don't think that's really true. I think the goal is really that you're not really interested per se in if the test is fair for both groups. You're interested in actually in the differences at the group level and if there are differences. Right? So you're interested in seeing if this latent variable here, eta, has a different distribution in group 1 compared to group 2. So what you're interested in actually is testing if the means are equal and if the variance covariance structure is equal between the groups. So if the placement of the center of this distribution is equal, if the spread is equal, and maybe even the correlation structure and things like that. Right? And one thing we can also do, I'll talk maybe a bit more about it later, is we can have a network at the latent level, for example, and then we can test if the networks are different or not. Which might be interesting as well. That would be similar to testing this test for homogeneity at the variance covariance structure. So if we did not have measurement error, and if we did not have multiple indicators, if we did not have our things to be latent, this would be similar to MANOVA test, box test, Levine test, things like that. Things you might already know, and things that were discussed in the undergraduate program for many psychology tracks as well. But now we can do this with taking measurement error into account, with having latent variables, so that's a very powerful thing. So I believe this is the goal. But, and we have a problem, the latent means are not identified. And the latent variances are arbitrary because they're scaling. So we just arbitrarily set it to 1, or we arbitrarily set it to, well, something, but that's just due to the first item being constrained, having a constrained factor loading. And we don't even know if this test measures the same thing in both groups. So that's what we might want to do. Oh. This is what we want to do, but we can't do it because, we already set it alpha to 0. So it turns out that we can solve this problem by sequentially imposing equality constraints and testing multiple levels of measurement invariance. And that means that the test measures the same construct in both groups. And we're going to do that sequentially. We're going to establish measurement invariance in steps, starting with configural invariance, then going on to weak, strong, and strict invariance. And each step that we take allows us to test more homogeneity hypotheses. So first, we're just simply going to test if the same structure generally holds in both groups. So that means that the factor loadings are similarly constructed with zeros at the same point. Next, we're going to set the lambdas to be equals, the factor loadings. Afterwards, we're going to set the intercepts to be equals. And finally, we're going to set the residual variances to be equal. And when we set these equality constraints, suddenly things become identified and we can test if the factor variance is the same or if the factor means are the same. So this is the concept of measurement invariance. And measurement invariance means that we can test if a test measures the same thing in two groups, or it measures the same construct, so it's not biased. And this is a very important topic in psychometrics in general. It's not just in CFA modeling, you also see it a lot in IRT modeling as well. And it's very important. So if measurement invariance does not hold, for example, then for sure we cannot use sum scores or test scores, and that's like a lot of psychometrics is about, but simply the sum score, to compare groups in any meaningful way, because the test is biased. If partial invariance holds, and that means that most items are not biased, but some might be, then we can still use multi-group CFA to test for these homogeneity invariance. It's a very powerful thing in CFA. We can actually take into account that some items might be biased a bit, and we can take it into account when testing for a homogeneity test. Right? But the more that invariance doesn't hold, we have to really think, okay, we're really fitting a different model in both groups, and maybe this comparison isn't fair anymore. The canonical reference for measurement invariance testing is this great paper by Don Mellenberg. And Don Mellenberg is at our department. He's now emeritus professor. You sometimes see him walking around still, but he's not around that much anymore. But this 1989 paper is really the canonical reference for measurement invariance testing in general. So if you want to read more about it, that would be the starting point. So measurement invariance is also explained in this really nice paper by Jelte Wiffers and Conrad Donen from 2010. That explains some really important concepts in detail, and also the steps that I show in the slides as well. So this is an example of a test item that's biased. So we have eta here. And this is basically our regression on the latent variable. Right? So here we have the item score, and the slope here is lambda. Right? So what we see here in group 1 and group 2, that the slope is the same, but the intercept is different. And what that means is that for the same level of the latent variable, let's say this is ability, group 1 will get a much higher score than group 2 on the test. And this is an example of uniform item, differential item functioning, as it's called. So uniform bias, where at least at every point in the scale here, the bias is the same. So it's always like, let's say 5 points or something like that. So we always have the same level of bias between the groups. It can get worse, and that's when also the lambda value is different. So here the factor loading is also different for the groups. And now we get some really weird things. So here, this level here, we get a very strong bias, while at this level we get a lesser bias. And then you can imagine that you can also even have a case where we have eta and we have two lines crossing, where for some level one group is favored, but for another lower levels another group is favored, and we get really weird things. And if you don't take it into account, definitely if you look at the sum score, we'll get mistakes. Okay, so let's start doing our sequential tests for measurement invariance. So first, we can look at configural invariance. And that's simply looking at if the same model holds in both groups. So then what we do is we simply fit this model that we had before with the constraints in both groups. We can do it in a single multi-group analysis. We can even do it in two separate analyses and then combine the results into one fit measure. But the software will allow you to do it in one go, which is nice. So let's look at this Holzinger-Feingold data that we've been seeing before the last week. And this was a data set where we had 3 latent variables, 9 indicators. We can draw the factor loadings. And we have correlation at the latent level. Let's say we have these factor variances here. Let's constrain the first factor loading to 1. We have residuals. And I added 2 parameters here. I added a factor loading from the first factor to the last item. And I added the residual correlation between item 3 and 5. And now we're also going to add the mean structure. So each of these also have an intercept. Let's just draw it like this, one, and then like an arrow pointing to all of these. So how many parameters do we have now in a single group model? Well, maybe you can pause the video for a bit here and think about that. Okay, so how many parameters do we have? We have at the latent level 6 variances and covariances. 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5, 6, 7 factor loadings. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 residual variances or covariances. And we have 9 intercepts. So this leads to a total of 32 parameters. So how many observations do we have? We have 9 items, so 9 times 9 plus 3 divided by 2 equals 54 observations. Right? We can also think about that as having 9 times 10 divided by 2 equals 45 variances and covariances plus 9 intercepts equals 54. But now in this data set, we're going to do a multi-group analysis because we have a grouping variable called school. And we actually have 2 schools, and we want to compare them and see what the differences are in ability between schools. Maybe one school is better at visual reasoning, where another school focuses more on the textual aspect. So how many parameters observations do we have then? Well, we can multiply this by 2 and this by 2 as well. So that's 64, and 54 times 2 is 108. So what's our degrees of freedom then? Minus 64 equals 44. So then our multi-group analysis would have 44 degrees of freedom. And this multiplied by 2 indicates the observations. You can always do that. Here, that's simply because we had no equality constraints. Right, so we could also draw on this per group and then discount which are the unique number of parameters. So that would lead to 44 degrees of freedom. Okay, so we can fit a configural invariance model, and there's nothing really special going on yet. If that model doesn't fit, we can pretty much stop there, because then it means that the vector structure does not fit in both groups. So then we already know that at least it's not measuring the same thing, it might not be measuring something at all. Right? So if configural invariance does not hold, we have a big problem, we cannot really get around that anyway. Now let's go for weak invariance. So the first step we can do is then impose weak invariance. And in weak invariance, we are going to constrain the factor loadings to be equal. So now, I have equal factor loadings across groups. So you see here that there's no more group subscript. Like this third subscript here indicates the group, it's no more there. So lambda 1, 1 and lambda 1, 1 here. So that means that I have 3 less parameters in this model. So here the degrees of freedom was 0. Now I have 3 less parameters. But at the same time, we can see that we identified this factor variance in group 2. And that's because the scaling now is already constrained equal, because we have identified the scaling in group 1. And this factor loading is equal. And this means that we cannot arbitrarily make lambda bigger and psi smaller, because in group 1 psi is already constrained to be equal to 1. And because of that, lambda in group 2 model, because it's the same lambda, also cannot arbitrarily become bigger or smaller and compensate for a difference in psi. And then this residual latent variance is identified. So we add this to the model. So we have minus 3 parameters in this case, but plus 1. And in the case where we did not constrain this factor variance to 1, let's delete everything. But let's say this was a vector variance that we were estimating. So this was psi 1, 1, 1, but this was 1 and this was 1. Then we would have gotten 2 less parameters in the model, but this wouldn't have changed, right? So then we would also have 2 less parameters in the model, the same as before. Okay, so let's look at our Holzinger-Swingold example again. So now we have a degree of freedom difference of 7, because we constrained 3 out of 10 factor loadings already to be 1. So now we constrain in group 2 all the other factor loadings to be equal to the group 1 one, so that's minus 7 factor loadings. If we would have done the scaling via the latent variance, then we would have 10 free factor loadings, but we would have added 3 factor variances in group 2, so it would be the same degrees of freedom difference as 7. So we can compare the weak model to the configural model with a test that we've talked about last week, in which is the test with 7 degrees of freedom, and we can get a chi-square value. We can also look at the differences in AIC and BIC if we want. So in this case, we tried to reject the hypothesis that these things are equal, and we couldn't. Right, so then we would accept the weak invariance model and move on. So the next step is strong measurement invariance. And in strong measurement invariance, we are also going to constrain the intercepts to be equal. So we already have these factor loadings equal across groups. And now we're also constraining these intercepts to be equal across groups. And again, that leads to a difference of -3 parameters, because we don't need to estimate intercepts per group. We only have one set of intercepts we need to estimate. And again, because these are equal, now suddenly the mean at the latent of the latent variable in the second group becomes identified. And it's the same idea as before. Because this threshold is already identified in group 1 and is equal in group 2, it cannot grow arbitrarily in group 2 to compensate for differences in alpha. So this alpha is now identified, which is a really nice thing. So that means we still need to identify a mean to 0, one group, but we can look at differences between this mean and other means. So for the other group, we can look at the difference, for example. So that's what this parameter tells us. How much higher or lower is this mean in group 2 compared to group 1? So we have -3 intercepts plus 1 parameters is again -2 parameters. So in our Holzinger-Swingold dataset, we can do that again. And what in Lavaan you say group equal. I have a video series on measurement invariance testing in different software packages, so I won't really talk about that now. And the degrees of freedom difference would now be 6. So we have 9 intercepts. We had 10 factor loadings before because of the cross loadings. That's why it's 7 before. But now it's 6 because we lose 9 intercepts, but we gain 3 latent variable means that we need to estimate. And then we can compare that. So let's see if strong invariance holds. And we get 3 asterisks, which is very, very significant, like a p-value of very low. Pretty high chi-square difference, right? That's why this p-value is low. And also the BIC and the AIC are, well, the BIC is actually better for, no, the BIC is better for the weak invariance model. And the AIC also, yes. So in this case, we would actually prefer the weak invariance model over the strong invariance model in all these measures. That might be a bad thing. So that indicates that there is a violation of measurement invariance in this dataset. So now, ideally, we would find where is the difference in measurement invariance. And there are multiple ways you can do this. One way is simply looking at the implied versus the observed mean structure. Another way that you can do is to use modification indices. And in psychokinetics, for example, you have equality constraint free modification indices that can help you with that. Lavaan has another type of modification indices for that can also help you with that to find which parameters you can free from constraint to best improve your model. But the easier way to do it is simply look at the differences in observed and implied means. Right, so the LAF score test is the test in Lavaan for the modification indices actually, which is more powerful. So here we see, okay, so what we see here, we see a big difference here on x3 in group 1, and also on x3 in group 2, much higher than the other ones. And also x7 here has a quite big difference between observed and implied means, and maybe x2 as well. So then we can use that to test if we can fit a model where partial strong invariance holds. So now I freed the intercept for x3 and x7. That means that on these two items the groups can differ on their intercept. So that means we take into account that in one group, in this case a school, that item might be easier than in another school. And then we can fit this partial strong invariance model, which I call strong 2 here. And then compared to the weak model, the p-value is not significant, it's 0.21. And also the BIC is lower and the AIC is lower. So we prefer this model over the weak invariance model. And then we can also compare this to the model we had, where we did not have this free intercept. And then we can see it also fits much better than that. So then we can say we accept at least partial invariance here. And the more things you have to free up, at some point you're going to get partial invariance. But the more things you have to free up, the more you're moving away from invariance, and the more you might simply at some point say, okay, this test is just not fair. Right? So maybe one item is biased, but if you have like 5, 6 different indicators that we need to free up, then yeah, there's something really weird going on in the test. Right? So ideally, you have a test where you don't have to do this, but you can do it if you want. And that okay, and then the final step would be to establish strict invariance, and then we test if the residuals are the same. And this we actually don't need for the homogeneity test. For the homogeneity test, we're going to look at the means and the variances, and for that we only need partial weak and partial strong invariance. But this is still a useful thing to know. So this would mean that for one group, the spread would be much larger than for another group. Right, so the measurement error would be much larger. So that means that the test is much more precise in one group than in another group. And that would also be very useful information to know. But if strict invariance does not hold, that doesn't mean that we cannot compare people groups on their means anymore. Okay, so then we can do that in Lavaan as well. So we add residuals and the residual covariances here in the group partial. And there's some other ways to do this as well. And then in this case, it's questionable. Okay, so the p-value here, 0.03379. So yeah, okay, it's below 0.05. If we establish that as alpha, this would be rejection of the hypothesis. But the BIC and the AIC are actually better for the residual, for the strict invariance model. So it's debatable. Like, yeah, you can say, okay, this seems alright, but you know, there's something here. We might want to look at partial strict invariance, maybe, perhaps. But this would also be a model that we can work with. Okay, and now we have established at least partial invariance in this dataset. We saw that there was some bias perhaps in items 3 and item 7. But taking that into account, we can still get a quite okay model that we can use for our homogeneity tests. And that will be in the next video.